Good morning, everyone, and thank you to the organizing committee for inviting me to present our research on the application of pressurized liquid extraction, or PLE, to address two distinct challenges in food chemistry. On one hand, we evaluated its role as an analytical tool for the isolation of contaminants, and on the other hand, we focused on its optimization for the recovery of thermolabile bioactive compounds. In the current food science landscape, chemical analysts operate under competing technical requirements. On one hand, routine food safety monitoring demands low detection limits and high sample throughput for ubiquitous contaminants such as mineral oil, hydrocarbons. On the other hand, the functional characterization of agricultural products requires the efficient isolation of target bioactive molecules such as polyphenols, where preserving chemical stability and maximizing extraction yield are the primary goals. Conventional extraction techniques often struggle to address these parameters efficiently due to high organic solvent consumption, extended process times, or the inherent risk of thermal degradation. In this context, a careful optimization of PLE parameters can balance these operational needs, as I will show you through specific case studies spanning both food safety and bioactive mass isolation. To understand why PLE can be so effective, we must look at the thermodynamics of the system. By applying elevated pressures, generally restricted between 100 and 150 bar, we can maintain organic solvents or water networks in their fluid-liquid state at temperatures far exceeding their atmospheric boiling points. When a solvent is heated under these highly pressurized conditions, its viscosity and surface tension drop significantly, enhancing the diffusion coefficients of the target analytes, allowing for rapid fluid penetration into the deepest pores of the solid matrix. Furthermore, the elevated thermal energy provides the necessary enthalpy to efficiently disrupt the strong cohesive forces that bind the analytes to the active sites of the substrate. The ultimate result is an accelerated exhaustive mass transfer rate that traditional ambient pressure methods simply cannot match. Before evaluating our specific case studies, let us focus on the instrumental architecture that makes these thermodynamic parameters possible. As shown in this fluidic diagram, the PLE system is built around a robust high-pressure hydraulic network. A pump delivers the solvent or solvent mixtures into a stainless steel extraction cell, which is tightly sealed and housed inside a temperature-controlled thermostatic oven. Inside the cell body, the solid sample is never packed raw. It is systematically dispersed with an inert material such as quartz or sand or diatomaceous earth to prevent matrix compaction and eliminate preferential solvent challenging, thereby maximizing the available contact surface area. The extraction can be performed using a static mode where the solvent expands and dissolves the target analytes under equilibrium conditions, or by a dynamic flush where fresh solvent displaces the extract through a back pressure regular directly into the collection vial. To evaluate the role of PLE in food safety, we must first address the analytical challenges posed by mineral oil hydrocarbons, which are systematically categorized into mineral oil saturated hydrocarbons, or MOSH, and mineral oil aromatic hydrocarbons, known as MOAH. These fractions do not represent distinct isolated analytes, but rather highly complex ubiquitous mixtures containing tens of thousands structural isomers. Consequently, when analyzing these fractions via gas chromatography, the profiles do not represent sharp resolved peaks. Instead, they appear as massive unresolved complex mixtures that manifest as broad chromatographic humps. Monitoring these harms is critical due to severe toxicological concerns. While MOSH can accumulate within human tissues and organs, specific low alkylated polycyclic aromatic compounds within the MOAH fraction are suspected carcinogenic and genotoxic. Given that new European regulatory thresholds based on food fat content are scheduled to enter into force next year in 2027, and considering that migration from recycled paperboard packaging is a remarkable contamination vector into dry foods, establishing robust high-performance extraction methodologies is an essential priority for routine industrial compliance. As a direct consequence, a primary objective of our research was to design and optimize a rapid PLE protocol specifically tailored for cardboard and paperboard packaging materials. This monitoring is particularly critical when dealing with recycled cellulose fibers, which frequently contain high background levels of mineral oils due to residual printing inks, adhesives, and waterproofing additives. Differently from food matrices, cardboard do not require milling or dispersion with inert solvents like sand, but it was simply cut into strips and put directly into the cell. To minimize solvent consumption, an operational cell of 10 ml was selected along with stainless steel expansion elements positioned at the bottom of the cell. Traditionally, during overnight extraction, hexane ethanol mixtures are preferred because ethanol swells the polar cellulose matrix, releasing entrapped fractions. However, under pressurized conditions, this kinetic limitation disappeared. Pure hexane demonstrated excellent affinity for the lipophilic hydrocarbon fractions while leaving the polar cellulose matrix undisturbed, and the ethanol introduced an analytical drawback requiring a tedious post-extraction water washing step followed by centrifugation to isolate the phases. Moving deeper into the kinetic method optimization, we systematically investigated the combined effects of extraction temperature, static hold time, and the number of operational cycles required to guarantee exhaustive recovery across highly variable packaging structures. When optimizing temperature profiling from 30 to 70 degrees, we carefully monitored the risk of thermal discrimination. While elevated thermodynamic regimes accelerate desorption kinetics, going too high poses a distinct risk of losing highly volatile hydrocarbons. Our experimental data showed that a temperature of 60 degrees combined with a stable system pressure of 100 bar represents the ideal thermodynamic compromise. Regarding the static extraction duration, doubling the time from 5 to 10 minutes showed no operational benefits, allowing us to lock the parameter at exactly 5 minutes to maximize sample throughput. However, as shown by the chromatographic overlays on the left, a single extraction cycle is mathematically insufficient for use in regulatory monitoring. One cycle yields varied sharply between 76 and 100%, demonstrating a direct dependency on physical cardboard thickness and density. Paradoxically, a thinner substrate retained more analytes than a thicker matrix during a single static expansion, likely due to tight pore compacting. To overcome this, we evaluated whether an automated 5 ml solvent wash could bypass a second pressurized block, but the results matched the incomplete one-cycle profile. Ultimately, a definitive two-cycle pressurized extraction protocol was applied. This operational setup consistently achieved total quantitative recovery across all cardboard typologies, leaving less than 2% of total residual contamination in a third validation cycle, while reducing total sample preparation time to less than 30 minutes, with relative standard deviation consistently below 5%. When we move our focus from packaging materials to dry food matrices like semolina pasta, a fundamental question arises. Is it possible to distinguish between recent superficial hydrocarbon migration originating from paperboard packaging and endogenous background contamination already pre-existing within the raw material due to environmental or processing factors? To answer this question, we developed a dual-mode PLE strategy, specifically comparing a superficial method against a total method. For the superficial method, our primary goal was to restrict solvent penetration. To achieve this, we utilized a whole, completely intact pasta sample, extracting with pure hexane at 100 degrees and 100 bar for a single static cycle of 5 minutes. In this way, the organic solvent rinses only the outer layer where migrated motion MOAH accumulate, leaving the compact internal core completely undisturbed and providing a rapid total extraction time of less than 20 minutes, with an average recovery of 97%. Conversely, to determine the total contamination, the analytical process was intensified. Here, the pasta sample was finely ground into a powder to maximize the surface exposure, and we introduced a binary solvent network composed of hexane and ethanol in a 1-to-1 volumetric ratio. Furthermore, the extraction at 100 degrees was programmed with 2 static cycles. In this setup, ethanol acts as a polar modifier that induces a significant swelling effect on the highly crystalline structure of the matrix, ensuring that the solvent gains complete accessibility to the internal analytes trapped deep inside the pasta core, driving an exhaustive desorption. Furthermore, as visible in the overlaid chromatograms, this total method allowed for a higher recovery of contamination compared to what was typically achieved using traditional extraction protocols. The chromatograms generated by the superficial method revealed a sharp, low-boiling hydrocarbon envelope, tightly restricted between C14 and C24. When optimizing this step, tracking temperatures from 80 up to 120 degrees demonstrated that raising the thermal threshold inside the cell caused a progressive, unwanted migration of the internal matrix lipids and active hydrocarbons into the solvent. In contrast, the total method yielded a completely different chromatographic profile characterized by a high boiling hump extending far beyond C25 that represents the pre-existing endogenous background contamination. The true analytical power and potential of this platform lies in its sequential application. By implementing first the superficial method and subsequently the total method on the matrix, we can generate highly complementary data, allowing to cross-reference the exact contamination fingerprint, effectively discriminating packaging-related migration from core-embedded background pollution. Now, let us completely shift gears and redirect our focus toward an entirely different objective, the targeted recovery of bioactive molecules, such as phenolic compounds. In this case, we are dealing with high-polar thermolabile plant metabolites. To ensure exhaustive recovery while strictly preventing thermal degradation pathways, we must exploit the tunable properties of green solvent networks, such as subcritical water-ethanol mixtures. Under elevated pressures, adjusting the temperature allows for precise manipulation of the solvent's dielectric constant, effectively mimicking the solvation behavior of classical organic solvents. In a recent study, we targeted green pea flowers, which represent the actual key ingredient for innovative functional food formulation. To fully understand the impact of industrial processing, whole green pea seeds and their hulls were used as agronomic references. Our primary objective was to develop a high-efficient extraction protocol to recover phenolic compounds by using PLE, using a green solvent network composed of an ethanol-water mixture at a 70-to-30 volumetric ratio, overcoming the complex carbohydrate-protein cellular architecture of the P, which can embed the target compounds. To systematically evaluate the behavior of PLE on these bioactive fractions, we implemented a central composite design backed by response surface methodology, evaluating the simultaneous effects and cross-interactions of extraction temperature and static hold time. Results highlighted how accelerating the thermodynamic parameters promotes the rapid desorption of bound phenolics from the protein carbohydrate matrix. Concurrently, however, the model precisely maps the operational boundary where excessive thermal stress or overexposure leads to destructive structural degradation pathways. This physical phenomenon is visually reflected on the right-hand side of the slide by the distinct color change in the extract vials. As we approach 140 degrees, the extract shifted from green to a dark brown, marking the threshold of thermal penalty. The mathematical model converged at an optimal temperature of 122 degrees and a static extraction time of 17 minutes for 3 cycles, under a stable system pressure of 100 bar. A 5-fold increase in total phenolic yields compared to conventional solid liquid reference protocols was observed under these conditions. From a physiochemical standpoint, operating at 122 degrees provides the precise activation energy required to alter the cellular matrix and systematically cleave the strong hydrogen and covalent bonds that trap target polyphenols within the complex protein starch architectures. The PLE fractions were then subjected to high-resolution MS profiling, revealing a fingerprint of bioactive compounds. 18 distinct compounds belonging to the flavonoid and phenolic acid classes have been successfully identified. P flowers are dominated by rutin among the flavonoids and quinic acid among the phenolic acids, molecules of both nutritional and therapeutic value. To conclude, the systematic data gathered across our investigations confirms that PLE represents a highly robust, versatile, and automated platform for modern food chemistry. Regarding food safety and contaminants, PLE proved to be a highly effective tool for trace isolation, achieving the discrimination of packaging-derived hydrocarbon migration without penetrating the internal matrix core, while an intensified two-cycle protocol using hexane ethanol guaranteed exhaustive rapid recovery of both MOSH and MOAH fractions. Regarding bioactive compounds, the platform demonstrated outstanding efficiency in recovering thermolabile high-value bioactive molecules from pea flowers. Backed by response surface methodology, we successfully balanced accelerated mass transfer kinetics against thermal degradation, achieving a 5-fold increase in total phenolic yield while rigorously preserving the structural and therapeutic integrity of key molecules like rutin and quinic acid. Regarding future trends and scalability, the true strength of PLE lies in its thermodynamic flexibility. Simply by selecting proper temperature, pressure, and solvent networks, the same hardware transitions from trace environmental isolation to subcritical biomass upcycling. Finally, I would like to thank my research group and you for kind attention.